Chapter 16 presents statistical power and concludes with some other selected topics. Statistical power, or more formally, the statistical power of a significance test is the probability that that test in a given situation will reject a false null. Statistical power and beta are opposites. Given a false null, power is the probability of making a correct decision, rejecting that false null. Beta is the probability of making an incorrect decision. That is, of making a type 2 error, failing to reject the null even though that null is false. Power and beta sum to 1. Here is a formula to that effect. For instance, suppose that beta equals 0.40. In that case, power equals 1 minus 0.40, that is 0.60. Statistical power has a lot to do with sampling error, and as you know, as sample size gets larger and larger, sampling error tends to decrease. Now think about the situation when sample size is very small. In this situation, a great deal of sampling error is likely present. In other words, the study sample result may differ a lot from the population condition just due to the luck of the draw. Now in essence, in this situation, the significance test is trying to determine whether the difference between the study result and value stated in the null, whether that's reflecting a real difference or whether that difference is simply due to chance. Now there can be so much sampling error that in essence the job of the statistical test gets to be extremely difficult. It's trying to discriminate. Is the reason for the difference chance or a real difference? But if there's so much chance there, it's very difficult to determine the reason for the difference. And you can think about the analogy of a needle and a haystack, with the haystack representing sampling error, the noise that makes it difficult to find that real difference, which is the needle. So in essence, when sample size is very small, the haystack, which is to say the sampling error, can be very large. In this situation, finding the needle, which represents the real difference, the size of the real difference, if any, is difficult. So in this situation, power is almost always low. In other words, it's difficult to find the needle. It's difficult to get that large amount of sampling error, the haystack, out of the way. So here we are continuing to build on our parenting skills example from the prior chapter. I mean, we've changed things. We're supposing a different result. We're supposing that our study sample mean equals 97. And let's look at the sampling distribution we would get with different sample sizes. So the top distribution shows the sampling distribution when sample size is 100. Now in this distribution, the standard deviation of the sampling distribution approximately equals 2, and that's derived by taking the standard deviation in the sample and dividing by the square root of 100. So 20 divided by the square root of 100 yields 2. So the sampling distribution is showing you the distribution of results that you'd get with a true null. Now, when sample size is 100 and the standard deviation of the sampling distribution is 2, approximately 95% of the cases are falling between 96 and 104, plus or minus about 2 standard deviations. So in this example, the study sample mean is 97. So the study sample mean is not far enough to the tails of the sampling distribution for us to reject the null. It's not in a rejection region. So therefore we fail to reject. Now the middle distribution shows a sample size of 400. And so now we would be dividing 20 by the square root of 400. And the standard deviation of this sampling distribution would therefore equal 1 rather than 2. So the sampling distribution now has become a narrower one. Let's go ahead and look at our study sample result. Our study sample result is a 97. In this middle diagram, the 97 is indeed in a rejection region. It's pretty darn far off in the tail of the rejection region on the negative side of the distribution. So the message is with larger sampling size, we have less sampling error, or stated differently, a narrower sampling distribution. So the same study sample result now is out in the tail of the distribution and rejects the null. And if we increase sample size still further, say to 1600, and we'll presume the same results again, now look at the location of our study sample result. I mean, it's so to speak far to the left of the tail, but it's way out in the extremes of the negative tail. So with this very large sample size, now we get a clustering of sample means very close to the value stated in the null. So the basic message here is that as sample size increases, smaller and smaller differences result in rejection of the null. And you know, the basic conclusion is if the null really is false, you're going to stand a better chance of making the correct decision of rejecting that null if your sample size is larger. So the top part of the slide shows some things that I was just mentioning. Sample size can be so small that the significance test does not have a realistic opportunity to reject the null. And in such a situation, power is very low. Now let's get a look at a situation like that. So given a true null, what does the sampling distribution of the mean look like when n equals 9? Now I note that I'm carrying this example out for learning purposes. You shouldn't carry out a large sample test with a sample size of 9. Well, here is our sampling distribution, and we've changed the scale of the x-axis here, but to come out 2 standard deviations now in the positive direction, we've got to come all the way to about 113 or to about 87 in the negative direction. So with this very small sample size, the sampling distribution is much more spread out, and therefore study sample results much farther from the values stated in the null are required to reject the null. So this is basically a situation where power is low, where you need such a large difference to reject the null that in essence it's unlikely that you would get a difference that is that large. Now low power due to small sample size is a common problem in human services research. When sample size is small, the researcher often fails to reject the null, not because the null is true, but rather because power is low. And you know, when power is very low, in essence, you don't have a genuine opportunity to reject the null. Now let's look at an example where power is low. So suppose that you're working in a child welfare setting and an experiment is carried out. We have a new program that's designed to prevent placement, and then there is a traditional program. And so what we see is 10 kids go to each of these interventions, and that perhaps this is a placement prevention program, and what we see is much better results in the new program. Only 30% of our kids versus 70% in the traditional program need placement. So you can use difference in percentages here to get a feel for the size of association. So the size of association here is reasonably large. The difference in percentages is about 40%. So this is a large difference. Now, the statistical significance test that I carried out with this data was not statistically significant. So therefore, we failed to reject the null. The p from that test came out to be 0.13. So in other words, given a true null, the probability of getting this particular difference, or an even larger difference, and the true null would in essence state that the two programs have the same percentages needing placement. So the probability connected with the test comes out to be greater than 0.05, so we don't reject the null. So what's going on here is that sample size is very small. The total n is about 20. So in this situation, you'd need a very, very large difference in percentages in order to reject the null. And so a difference of 40% isn't sufficient, and therefore null is accepted. And you know, here you genuinely are left in a quandary. The large difference suggests to you, hey, maybe the new program really does work better. But then you do the significance test, and it shows you, well, you could get a difference this large or larger just by chance, by the luck of the assignment to the different programs, or in essence the luck of the draw. You could get that difference 13 times in every 100 samples. So the likelihood that the difference is due to luck alone isn't sufficiently small to reject. So it's sort of a quandary. There's good data suggesting the null may well be false, but that data isn't strong enough to reject. Now then, suppose the program was extended for another year, and so now we're going to up our sample size to 20, and we're going to presume that we are getting the very same results in terms of percentages. So we have 70% versus 30% needing placement, and this is a large difference. Now, when we carry out the significance test, the study result is statistically significant. P equals 0.009. So now the probability that the very same difference is due to chance is lower. And so what's going on here? Basically, sample size, increases in sample size increase the likelihood of rejecting the null. As you get larger and larger samples, smaller and smaller differences or weaker and weaker relationships become sufficient to reject the null. Well, we can say that differently than say other things being equal. As sample size goes up, statistical power goes up, the likelihood of getting a result that will result in rejection. So with very small samples, the problem is that your power is low, and that therefore you need very large relationships or very large differences in order to reject. Now with extremely large sample sizes, you can have the opposite problem. I mean, it's not really a problem. But the situation with very large samples is that very weak relationships or very small differences can be sufficient to reject the null. In other words, you can have a small difference. The test has so much statistical power, it can likely determine that that difference is not due to chance, and therefore you can reject the null. But perhaps the difference is so small that it's meaningless. So let's take a look at a situation that might be similar to this. Okay, in the special needs adoption study, the sample size was 600 or so. Now the correlation between adoptive parent reports of children's enjoyment of school and family income in the adoptive family was minus 0.10. Now, it's actually somewhat surprising that that's a negative correlation. You'd think that with larger income there might be a greater satisfaction on the child's part in school, but I mean, that's not the case. What I'm trying to demonstrate here more is that this correlation is a small one. This is quite a weak relationship. So it's a small difference. The question becomes, well, how can such a small correlation, and when the correlation is minus 0.10, if you were to look at the scatter plot, you'd just barely discern the negative slope of the dots in the scatter plot, and the dots would be very widely scattered around an imaginary line that would slope in a negative direction. So how can this very weak relationship be statistically significant? And the answer is that sample size is very large. Now, so when sample size is very large, sampling distributions tend to be narrow and compact. Another way to say that is that sampling error is likely small, that the effects of chance are minimal. And another way to say it is that you can be confident that the study result is indeed close to the population condition. The job of the test is to distinguish between real relationship and sampling error. And in essence, with very large sample size, we can be confident that there's very little sampling error, and thus quite small differences are sufficient to reject the null. So this weak relationship is sufficient to reject the null, and the reason such a weak relationship is significant is that sample size is large, and therefore the likely amount of sampling error is small. And let's give you the one example from the book that really drives this point home. I remember in my graduate work the professor talking about a difference between female scores and male scores on some academic achievement area among high school kids. And the difference was a difference of only about, I think, 1/20th, or maybe even less than that, of a standard deviation. I mean, it was a tiny, tiny difference, much smaller than our definition of what a small difference is in terms of the difference in standard deviations. So there was this tiny, tiny difference. So how could it be statistically significant? And this achievement test had been given to hundreds of thousands of kids, so that there was virtually no sampling error. The sample was so very large that we knew that the population difference was exceedingly close to that result in the sample. So the null that girls and boys were means in this achievement area were equal. We rejected that null. And we could be confident that difference wasn't due to chance. So what's potentially misleading in this situation is saying to yourself, aha, the result is statistically significant. And that does indeed convey that it's unlikely to be due to chance. But it's not always the case that a statistically significant difference is a large difference. So for instance, this difference was a very trivial difference. In a pragmatic sense, the degree of difference was such that one could consider girls and boys to be equally proficient at this particular academic skill. But I mean, in some, with very, very large sample sizes, Statistical power is often very, very high, and tiny differences are often sufficient to reject the null. So now what we need to do is, in the next video, is look at some factors other than sample size that affect power.